The force of gravity is so much taken for granted it's a real challenge to teach about. Today, one teacher has kindly agreed to let our cameras in to share one of her first lessons of the autumn term. Yes, it's a tricky one.
Okay, it's Monday morning. We've got Year 6 Science. Hopefully, understanding the terms mass, weight and gravity. We'll have to see how it goes. Here I go. Okay, books out. Date and objective, please, both underlined. You can write the keywords in a colour if you want to, if you've got one there. If not, don't worry. It's the first lesson in the topic of the forces. It hasn't been taught before in the Year 6. There will be a small group working with a teaching assistant to help their scientific understanding in a discussion sort of environment. Quite apprehensive in a sense of the force meters and things like that, because I haven't done a practical activity in that sense where they're going to be getting up and about the classroom. And in terms of the lesson, the forces lesson, quite confident with the science, but I think I have to make sure that my understanding is very clear with such difficult concepts that I need them to understand. Something connected to what we're going to look at today, and we said that hopefully by the end of the lesson we'll understand the terms gravity, mass and weight. I'm hoping that you can use the words when we're talking accurately, which means you don't get them mixed up, okay? I'm also hoping when we use some equipment later that you can show you can use it safely. This, using your imagination this morning, is our Earth. Okay? Our Earth. And that'll stay there. What might this be? Other than the pink ball. Imagination switched on. What might it be, Beth?
Pluto.
Not Pluto?
Moon.
The moon. Our moon. Okay? These two work together. The moon orbits the Earth. Putting the moon away for a minute. This is Astro Bear. Just come back from a flight. Now, our Earth. Astro Bear from the North Pole. If he jumps, where's he going to land? Sean?
In the South Pole.
She's going to do that. If you were stood up there, Sean, and you jumped up, where would you land?
In the same place.
In the same place, that's right. Exactly, the same place, okay. In China, Astro Bear jumps, where's he going to land? John?
Same place.
Same place, correct. South America, where's he going to land if he jumps? Lucy?
In the same place.
Same place. What is it that's making Astro Bear not fall off the world? Gina?
Gravity.
Gravity. Now, gravity is a force that pulls us where? Kirsty, what do you think?
In the centre of the Earth, so then it's like all around us. And
Something all around, so where does the gravity pull us to? Is it just to the ground or is there more?
to the like Earth core.
To the centre, doesn't it? So gravity pulls us to the centre of the Earth. It's a force, okay, a force that pulls us downwards. Gravity's different here and here. Tom, what do you think? Will it still pull him?
It pushes him upwards. On the moon, when he jumps, he goes higher and stays there for longer, and then he comes back down. Like the mass is like pulling us to the ground, so when we jump, it's like an elastic band tied to our feet, because when we jump, we always come back.
On Earth, the gravity is pulling you down, but on the moon, there's hardly any gravity. So you're more likely to float.
When you're on the moon, the gravity changes, so when you jump, you just high, and you just stay there for like a couple of minutes or something.
Megan?
Is it like magnets? Because when you put a south pole and a north pole together with magnets, they both like connect. And if you put weight and gravity together, they'll work together to pull you down.
The thing that keeps cropping up, and I know this links back to your work from last year, is all this idea about magnets and forces and all that thing. Well, you're absolutely right with magnets and forces. Magnetism, north and south poles, all those sorts of things. Turn to your partner very quickly now and say, and discuss with each other, how is it that this is different? You've said it's different. There is something different about gravity here and here. I wonder if it's something that you can tell me before I tell you.
When you're in Earth,
you'd only jump up for a short amount of time, then come straight back down.
But if there's not much gravity on the Earth, we would be able to jump far higher, wouldn't we?
The Earth makes its own gravity, so what does the moon do?
Make its own, but it can't make as much as the Earth because it's only small.
Brilliant, that's right.
Interesting things I've been hearing. This table here, which was quite nice, I've linked back to things that you remember from last year.
The bigger the planet, the more gravity it'll have, because on Jupiter you could hardly move your feet, you could hardly walk. But if you went on Pluto, because it's the smallest planet, you'd be just floating if you just sort of did a tiny jump.
So the amount of gravity, or I'm going to throw a new word, gravitational pull, is different according to the size of the planet. Weight and mass, that's where we're going to go next. Now, our bear, Astro Bear, has our bear from here to here been on a crash diet? Has he stopped eating junk food? Has he then decided to lose a lot of weight? Megan, what do you think?
No, it's he hasn't changed or gone on diet or anything because it's the gravity that it's the mass.
And this is where it gets a bit confusing, and I don't think we help in our outside world, in the real world, that when you would go and measure apples or bananas, you would use grams and kilograms. Problem is that weight shouldn't actually be measured in grams and kilograms, or not shouldn't actually be measured, but the measurement we use to measure it, because it's a force, is newtons. His mass doesn't change, but it gets confusing because we all talk about weight and we say what the things weigh. And you weigh yourself, and you weigh fruit, and you weigh things when you go shopping and things. But it gets a bit confusing because his mass doesn't change, the amount of stuff he's got in him, but the weight changes because the force changes. There is less force pulling him here than there is there. Newtons. Anybody recognise that name? Newtons? A famous gentleman, I think, linked to Newton. Go on, Tom. Newton.
Was it Isaac Newton?
It was Sir Isaac Newton. And what was Sir Isaac Newton famous for?
Did he discover gravity?
He did. He's a gentleman that studied gravity and forces. So when we talk about forces, and gravity is a force, and weight is a force, then we use newtons as the measurement linked to Sir Isaac Newton. Brilliant. What changes? We said something changes in Astro Bear. What changed, Sam? His mass or his weight?
His weight.
His weight. Why and how?
Because of the gravity. Because the Earth is bigger and the Moon is smaller.
And why does that affect the gravity?
Because there's less gravity on the Moon than there is on the Earth.
Brilliant. Now, keywords that we've got. Well, I can add some keywords in here already, because they're the keywords that we're going to use. Gravity, mass, and weight. Are there any more keywords that anybody thinks I can add now? Tom?
Gravitational pull.
Oh, brilliant. Great keyword. Well done. Kirsty?
Force.
Brilliant. Gina?
It's newtons.
Newton's excellent. What else could I have, Megan?
You can have kilograms and mass.
Excellent, because we've got those two that would link together, wouldn't we? Newtons and weight, kilograms and mass. What's this? It's got grams on one side and newtons on the other.
Is it called a Newton meter?
Excellent. What do you think a Newton meter, or you'll find that you said force meter. Now, there's a clue in both of those. What do you think that is going to measure? Ben, what do you think it's going to measure?
Newton.
Newtons, so it's measuring what?
Weight.
Weight, excellent. It's going to be the measure the weight of an object, and we're measuring the weight as a force, how much pull there is going to be on that object. And you're going to explore lifting up different things to measure the mass and the weight.
The force meters have different scales, so the children are having to choose carefully to get accurate readings.
Newton 225.
Looks good.
Then back. Okay then. 30.
Is that scale any more accurate than you did before?
It says 20. It was 4 in newtons.
Does it go away something?
Yeah, what should we do? This one. It is grams.
Right. So which are you looking at now? Are you looking at weight or mass?
And newtons in a gram. Times 10 will be 300.
Anybody got any measurements? Tony, I'm going to pick on yours. And what did you measure the globe to be?
9.
9 newtons. Did anybody else measure this globe? Weigh this globe, I should say. Or check the force pulling this globe down. Anybody else do this one? Kirsty, did you do this one as well?
Yeah.
And what did you get it to be?
I got 9.
Good work. So we've got accurate readings there. Anybody work with a chair? Sam?
It was 30.
Go on, help him out, Tom.
Well, it's 30 newtons and
Yep.
300 grams.
OK, we'll come back to that in a minute because you've got grams drawn down there as well. Maddie?
We did the chair as well, and we got 30 newtons and 300 grams.
In your books, what I'm going to want you to do is, I've got up on the board 3 sentence starters, really. But I would like you, using all the things that we've talked about. Now, Astro Bear, our little friend, was somebody that helped us to think about mass and weight. We've also got the equipment that we have used that is connected to weight. We've got all our keywords up on the board. When you open your books up, what I'm expecting to see in there are some description of what you've learnt about those 3 things today.
What else can you say?
To the centre.
Mass is the stuff we have inside us.
Wow.
Gravity on the moon is so little compared to the amount the Earth makes.
No, I've got it in the first.
Gravity is a force pulling everyone to the centre of the Earth.
Then can't you?
Mass is showing the size of something. It does not ever change.
It is gravitational pull on, what did we say, the Earth?
Weight is a force, and we measure it in newtons.
I think we've done extremely well today. The discussions have been fantastic, and just generally people trying to do the right thing and talk about the right words is very good. This table can put chairs under and you can go. There was quite a few children that surprised me with their enthusiasm for such a difficult topic, the children at the lower end of the class, ability-wise, that found literacy skills difficult, but were fully involved in the lesson, so that was quite pleasing. Know for definite that I will definitely have to pick things up again, beginning of the next lesson. The starter will have to be looking at any misconceptions that have arrived from marking their books, but generally overall quite pleased. I thought the children did very well today.
Zoe began by modelling the Earth and Moon with Astrobear to help the children understand gravity.
Gravity is different here and here.
Zoe's next challenge was to clarify what weight and mass mean.
The weight changes because the force changes.
She then involved the whole class in
Oh,
identifying
brilliant, great,
keywords.
well Kirsty?
Force.
Brilliant.
Using force meters and writing up their findings consolidated the learning objective. Finally, Zoe presented the children with 3 open-ended questions to test their understanding.